Hello everybody, welcome to the second part of our talk about radicals, and we're going to learn about radical halogenation, why it's super useful, and then the types of different radicals that we can use to halogenate hydrocarbons. So radical halogenations, here is an example of a radical halogenation. What we are going to see is that we're usually going to start with some sort of hydrocarbon. Right, there's no real other functionality on here, it's just hydrogens and carbons. And what you turn it into is you turn it into an alkyl halide. And now this is really great because hydrocarbons, we don't know any chemistry that we can do to hydrocarbons, right? You can't do SN1, SN2, you can't dehydrate an alcohol, you can't, add HBr to it, there's no alkene, right? These are pretty unreactive. And in fact, to us at this point, they have no reactivity whatsoever. We don't know how to do anything to them. But if you turn it into an alkyl halide, now we can do all kinds of things, right? Now we can do E2, SN2, SN1, which means I can turn things into an alkene. I know a bunch of reactions that I can do to alkenes. There's just all this other chemistry that just opens wide up as soon as you can get a leaving group on there. So the real nice thing about these radical halogenations is that they add functionality. They add a good functional group to an otherwise unreactive molecule. And of course, they're called radical halogenations because we add a halogen here. And you're going to see that pretty much all of the time, except for NBS, but pretty much all of the time, we're going to add the straight up halogen. So the Br2, Cl2, I2, something like that, right? We're going to add the actual halogen. So let me just do kind of just a generic example here, just to kind of emphasize some other things, right? So we're going to have just some sort of X, whatever that X is. And let me just make this a cyclopentane. You're going to add your X2, and you're going to add some sort of initiator. Because all of these reactions, they need to get going somehow. All right, they need to get going somehow. And so these initiators are either going to be light. And so you either see light written out, or you'll see the H nu, which is what I have up here. This is supposed to be H nu up here. So you'll see H nu, which is just another way to abbreviate light. Or you'll see sometimes even just heat. Sometimes heat can break down some of these really unstable radicals. Or you'll see peroxides. Those are good initiators. So peroxides, right? So anything that has two oxygens connected to one another, right? That's the peroxide piece, the OO bond. Or there's all kinds of other things. There's other examples. AIBN is an example. If you see some weird acronym with your X2, probably that's an initiator. I don't care that you know what AIBN looks like, but there's just lots of different ways to initiate these reactions and to make the radicals that are going to start doing the reaction I'm going to show you in the next slide. But the idea is that you're going to, don't want to start with the halogen on here. Let me erase that. You're going to start with just cyclopentane. And the idea is at the end, you are going to get your halogen on here. So you're going to put your halogen on there, whatever it is, and you're going to have HX. So these solutions get acidic. You make, if you're doing chlorine, it's going to be hydrochloric acid, or bromine, it's going to be hydrobromic acid. So that's kind of your overview for the radical halogenation. Again, you start with the hydrocarbon, and you end with an alkyl halide. That's what we're looking for. So how do these reactions occur? The radical halogenation mechanism is going to look very different from your normal mechanism. And we're going to see that it has three types of steps. And these three types of steps are going to be your initiation step, your propagation steps, and your termination steps. Your termination steps. So there's going to be three types of steps. And then within these different phases or steps, there may be more than one in them. And I'll show you what I mean here. So we're going to take a look at this simple example right here of just turning propane into 2-bromopropane. Right, and again, you'll notice that I have here, right, I have just my Br2 as my halogen. I'm picking a solvent. Don't stress out too much about the solvents, but usually you pick a solvent that can't undergo radical halogenation itself. So really, halogenated solvents work well. And then I have light again here. So I'll draw the mechanism for this one. So in step one, the idea is that we have to make the first radicals. So make the first radicals. So I'm going to start with my Br2 because I'm using light. So I've got my Br2, I'm going to draw that all out, right? This is a mechanism, so I got to draw all of these electrons. And what we said is that we're going to use light. We're going to use light, so H nu. And what's going to happen is that when light hits these halogens, it's actually going to split this. I'm going to draw the electrons here a little bit in that double bond, or in that single bond. And it's going to split so that each electron goes to one of the atoms. And one of the things you may be noticing here is that I'm using a single-headed arrow, or a single hooked arrow. So it looks like this, right? It's not doubly barbed, it's a single barb. So it's a single hooked arrow, and what that means is that you move only one electron, right? Previously, when you use a two-headed arrow, that means you move two electrons. For radical reactions, we are going to be moving one electron at a time because they're radicals. We're going to move one electron at a time, and so we use single-headed arrows this whole time. And it's just for radical reactions, whether they're halogenations or other ones. So you don't use double-hooked, double-barbed arrows. You use single-hooked. And so what that means then, right, is the bromine on the left still has its lone pairs. But this electron right here, right, of the two electrons in this bromine bond, this bromine-bromine bond, this electron here ends up staying with that bromine. So I'm just going to draw that one electron on the bromine. And then same thing for the other bromine radicals. So Br. And now the idea here is that I have two bromine radicals, right? And they're radicals because they just have an unpaired electron, right? They have this single unpaired electron, making them radicals. Now, often in initiation steps, you see that you go from no radicals to two radicals. So if you see that, chances are it's an initiation step. So what becomes of these two bromine radicals, right? From here on out, I'm just going to draw one of those two, but we just produced two bromine radicals. So let me redraw one of them. And we had our propane, and I'm going to draw my propane out here, just so you can see the hydrogens and everything. And if you look at the product, I said that what's going to happen is that we're going to react at that secondary carbon, it's carbon number 2. And I'll talk more about why that one and not the other ones later. But for now, I'm just going to kind of stick with that. And what we're going to see is that the bromine is going to abstract a hydrogen. And by abstract, what that means is that it's going to take, right, again, these two electrons that are in that CH bond. One of those two electrons is going to combine with the single electron, the radical electron from the bromine, to make a new BR-H bond, right? So now my bromine has abstracted a hydrogen. It now has that H. Those two electrons that I just drew are those two electrons right there. But that leaves the other the other electron in that CH bond to just sit on the carbon. And so what we get is we get another one of these propane molecules, only it's lacking that H, and we've made a radical. Right, so here we started with a halogen radical. Right, we have a halogen radical, and we end up with an alkyl radical. And that's common for these propagation steps. What you're going to see is you're going to have one radical on the left, and you're still going to have one radical on the right. It's just going to be a different type of radical. It's a different species. So you're going to start with one radical, you're going to end with one radical. That's the first of the propagation steps. What's going to happen in the second propagation step is now that radical, that alkyl radical I just made, is going to do some chemistry. So now I have that alkyl radical. It doesn't have a full octet. It has a reactive radical, a reactive electron. And so what happens is that leftover Br2, right, the stuff that didn't split, that Br2 that you added, that's still around, right? Very little of it split, but we just got enough to split to start this radical reaction. And so the idea is here, it's kind of a similar thing. Now we're going to have the carbon and the bromine form a new bond. And so I'm going to have the electron from this carbon combine with one of the electrons from the other bromine, and the other electron from that bromine-bromine bond is going to sit onto the bromine atom, the other bromine atom, which is going to give me two things. It's going to give me a new carbon-bromine bond, right, where I've just made that new carbon-bromine bond. And it's going to give me a bromine radical. Now you'll notice, right, that this bromine radical sure looks a lot like this bromine radical. And that's why these are the propagation steps. It's because it's the idea is that after the second step here, right, after you do this second part of the propagation step, this bromine radical could then go back and find some more unreacted propane in this case, become more HBr, you make the alkyl radical, that alkyl radical reacts with the bromine, makes the bromopropane and more alkyl radical, which then goes around and does this. And so these two steps just go round and round and round and round. So they propagate one another. It's like a chain reaction is the idea. So this is where most of the chemistry is happening. You just kind of go in this big old circle here. And that just keeps it going and going and going until the concentrations of these things start to go down and you end up with just mostly radicals. And that's when the termination step comes in. And there's lots of different ways you can terminate these. But the idea is that to do a termination step, you're going to terminate the radicals. So you're going to take two radicals and put them together. So you take two radicals, you're going to end up with 0 radicals. So you just take any two radical species from this mechanism that I just drew above, and you combine them. Right, so I could have a bromine radical, accidentally find a bromine radical, right? If I had those two combine, that's just going to give me more Br2, which is fine. That'll just kind of keep on reacting. But that in theory is a termination step, right? I started off with 2 radicals, and I ended up with no radicals. I have a Br2 molecule. Or I could have one of my bromine radicals, right, combined with an alkyl radical. That'd be convenient because that would just give me more product. Sorry, I'm trying to draw this out so you see all of the hydrogens, right? So I can have a bromine radical combine with the alkyl radical, and that's just going to give me product. I'm sure you're feeling in your notes right now why we like to do the line bond drawings and not Lewis for things. So many hydrogens. Right, so that'd give you more product, great. But again, I went from 2 radicals to 1 radical. And then lastly, I could combine 2 radicals, and I am going to get lazy for this one. I'm just going to draw the propyl radical and another propyl radical and have those combine to give me product that looks like this, right? So this would be the homo-coupled or the alkyl on alkyl coupling of these 2 radicals. So again, the termination steps just from 2 radicals to 0 radicals. So anytime you do a radical halogenation, you have these 3 sort of categories of steps. You initiate, which means you start to form a radical. You start to form them. And then the propagation steps is where most of the chemistry is occurring. It's where you go round and round and round, and you make more of the halogen radical that reacts with the alkyl halide, which makes more halogen radical, which reacts with the, sorry, not alkyl halide, the haloalkane. And you just keep on, not haloalkane, hydrocarbon, sorry. You just keep on going round and round and round until things terminate, which is just a combination of radicals. So you end up with no more radicals, and then the reaction is done, is the idea. Now, you'll notice right on that previous one, I put the bromine on that middle carbon and not on one of the end carbons, and there's a reason for that, and that has to do with selectivity. So when you talk about radical halogenations, there is such thing as selectivity. So different halogen radicals react at different rates and give us different amounts of different products. So if I took like this butane and I added Cl2 to it, and I added some sort of initiator, I wrote peroxides in this case, but it doesn't have to be peroxides. It can be light, it can be whatever. The idea is that the Cl2 is going to give you a mixture that is like 70%-ish this, and about 30%-ish that. So you do have a major and a minor product, but you have 30% of your material is just kind of garbage. You got to throw it away. You have to run a column, separate stuff out, or maybe do a distillation to separate stuff out. It's not that selective. You have a major product and a minor product. That's good, but not that selective. Whereas if you compare that to the bromination on butane, what you see is you see essentially 99% of it is just that product, and less than 1% of it is that product. So you have very, 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 very little. This is very minor. would take very little cleaning, easy to get rid of. You might not even have to get rid of it depending on what your reaction is. Very minor, and this is very major. And that has to do with the selectivities of these radicals, right? So let me write the radicals, right? So we're talking about F2, Cl2, Br2, and I2, right? Just walking down the periodic table here. And what we're going to see is that if you compare these, let me just put a little box around here, right? If you look at these, the most reactive halogen, and you should remember this from Gen Chem, the most reactive halogen is fluorine, the least reactive is iodine. And it just has to do with how electronegative it is and how much it wants electrons. So fluorine is the most reactive. So most reactive, chlorine is the second most reactive, bromine is the third most, iodine is the least reactive. Right? You'll see people, maybe you've had this done before on you or you've done it to someone, but people will just take iodine solutions and rub them on somebody to disinfect it before they, make a cut or give an injection or something like that. Like you can just rub it on someone and it's fine. It's just reactive enough to kill microbes. But you would never ever rub bromine on someone, for example. That will burn them bad. Chlorine gas, super corrosive gas, was a war gas. Fluorine gas is like even worse. It'll just kill people, breathe enough gas of it. It just rips you apart. So most reactive, least reactive. And as you might imagine, that is the inverse of the selectivities, right? So if you take a look at these, the idea is that the most selective one in theory would be iodine, because it's the slowest, and the least selective definitely is fluorine. But what we see here is that really we don't really use fluorine because it's too reactive. There's no selectivity at all. And it's super dangerous, really, really, really dangerous. And it turns out that iodine doesn't work. And I'm not going to get into all the energetics of every single step. You can find this in your book. They give free energies of each of the different steps, and you'll see that the iodine, it doesn't produce enough energy to sustain itself. And so you can't really do that chain reaction, all those propagations with iodine. So that means really we just have two options. We really just have bromine and chlorine. These are our two options. Right? We have the more selective bromine. Bromine is very selective, whereas chlorine is more reactive. So we're going to talk about why we might choose one versus the other. Do I need the halogen, the leaving group, to go in a very specific spot? Or do I need it to just kind of go anywhere and then I can do whatever? So let's look at some other examples about what I mean by that selectivity. Right, so if I do a chlorination, right, I use Cl2. In this case, I'm using benzoyl peroxide, which is just this. If you don't know what benzoyl is, it's a benzene with a carbonyl on it. So benzoyl peroxide, I'll just draw it out so you can see it. It's just another peroxide. It's going to help generate a chlorine radical, and then it goes through the same propagation steps as what you saw before. The problem with this, though, is that there's many different places the chlorine can go. And so if you look at all the different environments, right, all the different unique types of hydrogens on this molecule, on this 2-methylpentane, you'll see that it can lead to a bunch of different products, right? So there's no other methyls like this, right? There's no other methyls attached to CH2s, so that's unique. This is a different environment. There's no other CH2s that have a methyl and a CH2 on either side. That makes this CH2 different. There's no other CHs. And then these two methyls are identical to one another. There's no difference between those two. You could replace them with one another. You'd never know the difference. So these are 5 different environments. Which is going to lead to at least 5 different products. And I say at least 5 different products because I'm not even counting the stereoisomers, right? Because again, we said that chlorines could add on one face or the other face. So let me start drawing these, right? So I'm just going to call this position 1, 2, 3, 4, and 5. And so I could imagine, right, drawing this molecule out where I put a chlorine on a position 1. I could put a chlorine there on my position 1. Check. I could take chlorine, and there's stereo. Once you do that, now you have stereochemistry, right? Now all of a sudden, this becomes a chiral center. And so now I have to take in consideration the fact that, well, I could have one where this is a wedge, or I could have one where this is a dash, right? There's no chirality before, but there is chirality now. And again, that's just, if I put a chlorine at those carbon 1, right, in environment 1. Now I could put a chlorine on carbon 2. That's a little simpler just because that doesn't create a new stereocenter. So I don't have to worry about drawing 2 stereoisomers for that. So carbon 1, carbon 2, check, check. There is carbon 3. Oops. But if I put a chlorine on carbon 3, again, that's going to form a stereocenter right here. So I need to consider, well, what if it is a wedge, and what if it's a dash? All right, so I'll draw one where it's a wedge, and I'll draw one where it's a dash. And that's just 2 products that came from if I put a chlorine on that 3rd carbon there in that 3rd environment. Same story with number 4, also going to create a stereocenter. So I'm going to draw 2 products here, right? One where I have my chlorine coming out, one where I have it going back. Because again, those are both stereocenters. And that's carbon number 4, that's environment number 4. And then lastly, I could also put it on carbon number 5, which thankfully does not introduce a new stereocenter. So I don't have to draw anything new. And there it is on carbon number 5. So just if I take that one relatively simple molecule, the 2-methylpentane, I try to do a chlorination, I'm going to end up getting a crazy mixture of 1, 2, 3, 4, 5, 6, 7, 8 different products. 8 different products. And maybe I just wanted one of these, right? Like this would be a total mess. It happened quickly, yes, but it's not very selective. You get a lot of different products. Now, if I did that same exact reaction, but with the benzoyl peroxide, what we see is all I need to do is I just need to find the most stable place. I didn't say that before. Right, so when I say that bromine is selective, sorry, I should have mentioned this before. When I say that it's very selective, that means that the Br is going to add wherever the most stable radical would be. That means that, like in that example I did with the mechanism, I put the bromine on the secondary carbon in the middle, not the primary carbon, right? Because we know that secondary radicals are more stable than primary radicals, just like carbocations. If I look at this molecule that I have right here, if I call this carbons 1, 2, 3, 4, and 5, what draws my eye here is that this is a tertiary carbon. So I know that that is going to be the place where I have the most stable radical intermediate. And so as far as my products go, that is where I'm going to see my bromine go. And that's going to be it, right? Bromine is very selective. This is your major product. You do not get an appreciable amount of any other product. Most of it's going to be there. And so we use bromine when we really want just a lot of one product. It's going to be the most useful to you synthetically if you have a complicated molecule at all. We'll see it in some other examples in a second that chlorinations are great for if there's really only one hydrogen environment, only one type of hydrogens, yeah, you might as well chlorinate it because it doesn't matter where it goes. I'll show you that in a sec. So again, we're saying same starting material. The only difference is what halogen you have here. And if you do a chlorination, you're going to get a boatload of products. If you do a bromination, you're going to get one product, just wherever that bromine is the most stable. So let's see some examples here. This first one is a good example, right, where there's only one hydrogen environment on this cyclohexane, right? So cyclohexane, cyclohexane only has one hydrogen environment. right? All those hydrogens on that cyclohexane, they're all interchangeable. There's no difference between the one on the top versus the one on the bottom right versus the one on the top left, or they're all identical. So I just can put my chlorine anywhere. And this would be a good example of why you might want to do a chlorination, because it doesn't really matter where you put your chlorine. I'm just going to put mine here. Great. That's what you would get. Now you'd also get HCl as a side product. You can put that or not. For me, you do get it as a side product. But again, I look for the organic thing that you're trying to make. Now here we have Br2 and benzoyl peroxide. And I put this example up here because your eye should be drawn real quick to that tertiary carbon. But when we talk about radical stability, it's like the stability of anything else, like cations or anions. And so I also need to pay attention to the fact that this carbon is benzylic, right? Which means that it would stabilize a radical, just like it would an anion or a cation. It stabilizes a radical by delocalization. And remember that delocalization is such a powerful force that if you can go benzylic, even over a tertiary spot, And so my major product for this one would be where I put that bromine in the benzylic position. So this would be my major product for that one. Just because that radical is going to be the most stable radical I can form. Bromine is super selective for that. That's where you find it. Now for the third one here, and maybe, sorry, you should pause. Maybe you pause, try the next three here, right? So we've got 2 more examples. And you can try the synthesis one at the bottom. So go ahead and pause. I'll stop talking for a sec, and then I'll come back and finish these. So hopefully you gave these a shot. Now with this one, it looks like I do have more than one hydrogen environment here, right? I've got these methyls on the outside are identical to one another. You can't tell me the difference between a CH3 on one end or the other end. They're the same. These CH2s are identical. You can't tell me the difference between those. And then I have a CH2 here in the middle. So this has 3 environments. 3 environments. So I know, again, I'm going to get at least 3 different products. And so I'll draw those 3 products, right? I'll draw one where I have a chlorine in that outermost environment. I'll draw one where I have a chlorine on the innermost environment, actually, which would give me 2 stereoisomers, right? And I'll draw one where I have the chlorine in that very center environment. So in environments 1, 2, and 3 there. So I'd get 4 products if I did Cl2 on just that pentane. Now for this next one, looks like I have bromine, so I'm thinking selectivity again, not just throw a chlorine anywhere or throw a bromine anywhere. I'm thinking selectivity, and again I see a tertiary spot. Don't be too tempted if you see a quaternary spot. Sometimes I get students that are like, ooh, but that has even more groups, so that's even better, so I'll put a bromine there. And then what they end up doing is they draw some product that looks like this, where they put a bromine on here, and then your big concern should be the fact that there's 5 bonds here, right? So don't just go slapping something. There has to be an H on there that got abstracted in that propagation step. You need to have a hydrogen there. So really the tertiary spot is the best spot because you can take an H off, you can have a tertiary radical at that spot. That's where the bromine is. So then for that product, you just put a bromine there on that tertiary carbon, leave everything else alone. I don't have any stereocenters. That would be my only product. Now for this synthesis problem, right, we're trying to work backwards here. What I'm seeing with this is I have an epoxide. I know 2 ways to make epoxides, but they both ultimately come from alkenes. So I know that at some point this needs to come from an alkene, specifically this alkene. Right, I can use that alkene and either make a halohydrin and then add a base to do the epoxidation, or I can add a peroxy acid like MCPBA or something like that. So I'm going to choose a peroxy acid. I'll use CF3 C double bond O O O H. So I'm adding my peroxy acid. Anyone would work, as long as it's a peroxy acid. But I need an alkene, and I don't have an alkene to start with, right? I just have a hydrocarbon. There's no functional groups on here, right? I can't do an E2 to this. I can't do an SN2 to this because I don't have a leaving group on here. But The whole point of this video, right, is that we can take these hydrocarbons and make them useful, make them have functionality by putting a halogen on them. So I do know how to put a halogen on them, and then I can do my SN1, SN2, all that sort of stuff. So I guess I can make an alkene from this, but at first I'm going to need to get a halogen on here. And since I want some sort of selectivity, I'm going to go with the Br2. I'm going to go with Br2, and I'll just put lights as my initiator. I'll just write light this time. And that's going to put a bromine in the most stable spot. And in this case, bromine's better because I don't want to do a chlorination and get chlorines all over the place, right? I don't want to get chlorine everywhere. I need a bromine in one spot so I get the highest yield for the synthesis. And then from here, this should just be nice review from before when you did your SN1, SN2, E2. This is just a nice old E2 reaction. I want the Zaitsev product, not the Hofmann, so I'm just going to pick a small base. Let's just go with sodium methoxide or something, or hydroxide or ethoxide. Any sort of small base would do a nice E2 with this tertiary alkyl halide, and then I can do in my epoxidation. So I could go from step 1 to the starting material to the product in just these 3 steps. So I'll give a little better idea of the importance of radical halogenations. Definitely practice some of these mechanisms on your own. They're real weird because of this single-headed arrow business. They're unlike any of the mechanisms that you've ever done or any of the ones that you will be doing in the future. It's just radicals are the weird ones with the single-headed arrow thing, with the homolytic cleavage versus the heterolytic cleavage. So do some practice on this. I've got some worksheets online and everything. And happy studying and good luck.